In this video, we discuss the digital communication modules. At the transmitter, the message, normally it is continuous time signal. We call it EMT. For digital communications, we need to convert this analog signal to discrete time signal first. That is this module A and D. And this is analog to discrete time, not analog to digital. This module is achieved by sampling the continuous time signal. The sampling rate is determined by the Nyquist rate and whatever the guard band will require. After the sampling, the signals is passed through a quantizer, where this quantizer map the signal values into discrete levels. And this quantizer can be designed as a uniform quantizer and non-uniform quantizer. The quantization is a design module in digital communication systems. We normally design to maximize the S, Q, and R signal to quantize noise ratio to minimize the distortion for the quantizer. Another component in design, the quantizer is the coding of the quantization levels. We can use grid coding, which is a better choice for communication systems. Now the output of the quantizer, we have this 0 and 1s and 0 and 1. This is a message bit. We obtain the message bits at the output of the quantizer. In practical digital communication systems, we have source encoder and also channel encoder, but this is a separate course and this is a separate course, and we do not discuss in our course. Now this is a bit stream, that's the message bits here. And because antenna cannot transmit digital bits directly, 0 and 1s digital bits, antenna transmit signal by electromagnetic wave propagation. So eventually, this antenna will transmit waveform from bit stream, bit message to the waveform. We need to do pulse modulation. During the pulse modulation, digital zeros and digital ones are mapped into pulses. And this pulses is waveform. It's a function of time. For example, if I have 1 1 0 0 1 0 1 1 1, I use this pulse, and 0 I use this pulse. Okay. So this is digital 1, this is digital 0. So therefore, this is 1 and 1 as a pulse, and this is and 0. 1 and 1, 0 and 0, and 1 and 0, and 1 and 1. So this is pulse modulation. We map the digital bits into pulses. After this step, we do modulation. This modulation brings this waveform into high frequency band and pass through the antenna, and the signal being transmitted to the channel. At the receiver, suppose this is a receive antenna, the signal is suppose is received ideally. What is transmitted here, we receive at the receiver ideally is the same without any distortions, which means the channel is ideal. Because the signal being transmitted at the high frequency band, so we need to perform demodulation to bring the signal into the baseband. And then we apply pulse demodulation. And here we receive ideally those pulses. And these pulses, we need to perform pulse demodulation. We map these pulses into digital bits. So this is 1 0 1 1 0, and etc. And then if we perform channel encoding, we need to perform channel decoding. And then we need to perform digital to analog. This is a digital to analog conversion, and the signal goes to the destination. Next, let's discuss our lab. In the lab, we start with the bit stream, 0 and 1, 1, 0. Those are digital bits. We perform pulse modulation, and then this waveform of those pulses is being modulated into high frequency. We use BPSK scheme, and the phase is different for digital 1 and digital 0. We're going to discuss that in detail shortly. At the receiver, we perform demodulation by multiplying the same waveform at the modulation and pass through a low-pass filter. And we should obtain this waveform roughly. And then we perform pulse demodulation manually. We map this waveform by observing this shape of the waveform. We map it into digital 1 and digital 0. So this is a digital bits 1, 1, 0, 0, 0, 1, and 1, 0, 1, and 1. And this step is pulse modulation. We use these pulses to represent 1 and these pulses to represent 0. So therefore, if we plot here, there should be a line here. So this should be 0 line. The waveform has values. This may be some positive A. This values is negative A. There's some values here and some values here. We do the modulation by binary phase shift K. We achieve that by multiply this waveform, because this is A, this is minus A, by multiply by this cosine signal. So when it's positive, we multiply by this cosine signal. That's this waveform. But when it's a negative here, it becomes negative cosine. So this become negative cosine here. And now become 1 again. So it become cosine again. So therefore, we can say the phase of this modulated signal is changing either 0 or pi, depending on the signal is a digital 1 or digital 0. So therefore, the name of a binary phase shift came. So in other words, if we call this as a U of t, the phase of U of t that equals to 0 for digital 1. So when I write digital 1, I have quotation mark here, and pi for digital 0. So this is a BPSK. And this is a high frequency. It can be transmitted through the antenna now. In the lab, we have a master signal that's 8K. We also, and this 8K provides a clock for the sequence generator. And this sequence generator, the output of this sequence generator perform this pulse shaping stage. That's this stage here. And this pulse is being modulated using a cosine signal. That's a 50K, that's the carrier. And after multiplication here, we obtain this BPSK signal here. And then we're going to look at those signals at different channels. Now at the receiver, we multiply by the same carrier signal. We multiply by the same carrier signal. And then we pass through a low pass filter. This is a demodulated signal. We should say roughly similar shape of this waveform. It may be distorted a little bit because of low pass filter, but that's close. Next, we're going to perform pulse demodulation, and this step is achieved by manually in the lab. We're going to use a comparator to determine is it digital 1 or digital 0 being transmitted. There is an adjustable power DC supply this level to make the decision of 0 or 1s. That's this lab.